Sound waves are produced when any vibrating object compresses and stretches material around it. That is to say, sound waves travel quickly in liquid than in gases, but they travel faster in solids than in liquids. At high altitude, the speed of sound is less than at sea level. When you are far from the source of sound, you might see the action before you hear the sound. Likely, in storm, you see the lightning flash before you hear the thunder. How can the speed of sound be determined in air? The aim of this experiment is to determine the speed of sound in air. Requirement: colored water, tuning fork, resonance tube, a ruler, retort stand, and rubber band. Precaution: do not hit the tuning fork on a hard surface such as a bench, because this will lead to impure notes and sometimes may cause destruction on the tuning fork. The end correction of a tube is slightly above the open end of the resonance tube. To be accurate, we have to find two resonance positions so as to avoid end correction. Procedure: set the apparatus as shown in the diagram. This diagram. Next, adjust the length of the air column above the water level until the resonance is heard. Strike the tuning fork and place it just above the open end of the resonance tube, and listen to the sound until the sound is loud, and that now will be the first resonance point. So that is the resonance point. So the first resonance has been occurred at this length. Now read the height above the water column and record. So the first resonance has been observed at a distance of 18 centimeters above the water level. So record this value. After having the first reading, repeat for the first resonance and then record. And then find the mean of the two so as to minimize the error. For the second time, the resonance appears to be at 17 centimeters above the water level. Record this value and find the mean. Repeat this procedure so that you get the second resonance. Again, do it twice and find the average so as to minimize the error. Increase the air column by lowering the level of water until the second resonance is observed. The second resonance has been observed at a distance of 54 centimeters from the end of the resonance tube. Record this and repeat. Take the second reading so as to minimize the error. So the second resonance has been observed at a distance of 54 centimeters below the end of the resonance tube. Repeat the second so as to minimize the error. The second reading was again the same, 54 centimeters below the end of the resonance tube. Find the average for the first length, that is L1, and this will be 17.5 centimeters. The average for the second length, that is L2, this will be 54 centimeters. Then find the difference, L2 minus L1. This will give you 36.5 centimeters. Then record the value of the tuning fork used. In our case, the value is 456.1 Hz. So from this result, we can say that the first resonance, the air column above the water level was vibrating at fundamental tone. That is to say, the wavelength was, that is wavelength over 4, that is a quarter wavelength. This was equal to the length plus end correction. So at first resonance, we can say wavelength over 4, that is a quarter wavelength. This is equal to length L, then plus end correction. For the second resonance, the wavelength, this is 3/4, and this will be equals to length plus the end correction C. Let this be equation number 2. Now taking equation number 2 minus equation number 1, 2 minus 1. This will give you 3/4 of a lambda minus a half minus a quarter of lambda. This will be lambda over 2. That is a half lambda, half wavelength. This will be equals to C will cancel, will be equals to L2 minus L1. Let this be equation 3. Now, from the relation that velocity of a sound in air is given by V, this will be equals to frequency then times wavelength. But lambda, this equals to 2 in bracket times L2 minus L1. Velocity V, this is given by the formula 2F in bracket L2 minus L1. The frequency, this is given, it is here, and the difference L2 minus L1, we have calculated it, it is here. Substituting the values, the velocity of sound in air, this is 332.9 meter per second according to this experiment. So the velocity of sound in air can be calculated by using a resonance tube. Describe factors that may alter the speed of sound in air.
People see and hear by means of light and sound waves, but we cannot see light or sound waves as they travel across the space. The study of behaviors of waves is great important as it plays a great role in our daily lives. For example, reflection is used in examination of mirrors, measuring distances, and the sonar systems uses reflection to assist ships in navigating, communicating, detecting other vessels in water. Refraction is used in dispersion of light as well as in optical instruments, which are focus or spread lighting. For example, microscopes and telescopes. And in medicine, is used to determine the eye's refractive error. Diffraction is used to determine the crystal structure of materials and used in measuring coefficient of thermal expansion, clustering size, and the thickness of thin films in physics laboratories. Interference is applied when creating holograms. A hologram is a photograph of an interference pattern which is able to produce a three-dimensional image when suitably illuminated. Also, destructive interference is used in noise reduction systems such as earphones. The waves that can be easily produced are water waves, though other types of waves also can be produced. The aim of this experiment is to demonstrate reflection, refraction, diffraction, and interference of waves. Requirements: water, white sheet, power source, and the ripple tank. Ripple tank is apparatus which is used in the study of behaviors of waves. It has main parts like this part. This one is a transparent shallow tray which water is filled. This is lamp which is used to illuminate the surface of water and to project wave patterns on the screen and the ripple tank. This is the electric motor which is used to vibrate the wooden and the spherical vibrators to produce waves. This is a wooden bar or vibrator which is used to produce plane waves. These two are metal spheres which are used to produce circular waves. Now, to use this, we have to connect lamp to the power unit. Here is the place for connecting lamp. Now we connect. Also, this is for motor. This is the press for connecting red to red and the black to black. This power unit is switched on. Before we proceed, there are some precautions which are to be considered when conducting. First one, the motor must be run at low speed to produce clear waves. And the second one, you have to use a bright light bulb or bulb to illuminate waves to the screen or white board under the ripple tank. Procedures: pour some water in the ripple tank and set the ripple tank with the plane vibrator. Then place the white sheet under the ripple tank. Then Place a plane obstacle at an angle with incident to the plane wave. Switch on the motor and observe what will happen on the white sheet. When the waves meet the plane obstacle, they are reflected at an angle to the incidence, and that is the reflection. Substitute the plane obstacle with a curved obstacle. When they meet a curved obstacle, they reflected spherically. Means that the reflected waves will be spherical. As it observed on the screen. Press the curved obstacle with a narrow openings obstacle. When the plane waves pass through the narrow opening, they spread out. That is diffraction. Remove the plane vibrator with a plane vibrator with a single vibrator. Vibrator with a single vibrator which have a spherical metal. Place two source single vibrator and set them to vibrate. Place two source single vibrator and set them to vibrate. When the single source vibrator vibrates, there are dark and white bands which are formed. The two circular waves from each single source are produced, and these waves, when they meet together, are said to interfere. Replace a two-source single with a plane vibrator. Set a glass slab of at least 3 millimeters thick in the water on the part of the ripple tank. Switch on the vibrator. As the wave passes the glass slab, they change in the direction. Also, the wavelength changes, that is, reflection of waves. Therefore, a ripple tank can be used to demonstrate the wave properties such as reflection, refraction, diffraction, and interference. Now, what are the benefits of studying wave properties in our daily life?
Inspection of instruments such as harp or piano shows that it consists of several stretched strings which vary in length and thickness. Piano strings, for example, are caused to vibrate when tuned by using felt hammer. There are various instruments which can produce stationary waves when plucked. The length of the string, however, may be altered by fingering. The frequency of a music note can depend on various factors. The aim of this experiment is to determine the frequency of a music note. Requirements: slotted masses, tuning forks of different frequencies, paper riders, rubber band, and sonometer with accessories. Procedure: place the sonometer bridges at a distance of 80 centimeters apart, with one sonometer at 0 mark where the pulleys are found, and the other sonometer will be varied while the faces on. Keep the sonometer wire at a constant tension. Place at least 3 paper riders on different distances on the sonometer wire. By using a rubber band, and place the stem of the tuning fork on the sonometer wire. Then adjust the position of the second bridge, sonometer bridge. Now this is the place where the paper rider is thrown off. From this observation, we can see that the string of the sonometer and the tuning fork both vibrating with the same frequency. Now measure the length L between the bridges. From our observation, the length between the bridges is 31 centimeters. Now record the value of the length on the given table. Using the same procedure and by using different tuning fork with various frequencies, obtain different values of the length between the bridges, the distance where the paper riders will be thrown off, and record the observation on the table. From the table of results, we have frequency, length of the string, and the reciprocal length. Now, draw the graph of frequency against reciprocal of length. The nature of the graph of frequency against reciprocal of length has this nature. Now, from the results of table values, as the frequency increases, the length of the string decreases. This shows that frequency of the tuning fork is inversely proportional to the length of the string. Question: how does the frequency of vibrating string vary with tension?
When a current-carrying conductor is placed in the magnetic field, it experiences the force. The magnitude of the force depends on the amount of current flowing and the strength of the magnetic field. The aim of this experiment is to investigate that force which a conductor experiences. We require to have a horseshoe magnet, source of power. Here we have cells which can produce 9 volts, connecting wires, a switch, a stiff wire, a little stand for holding our wires, and a plier or wire cutter. Connect the circuit as shown here. We have the cells in series so that we get 9 volts. Then using the little stand, clamp the wires which are bent so that when we place our conductor would be free to swing. Then place the horseshoe magnet in this position. After that, take your wire, bend the stiff wire to form a rectangular shape. Then the ends of this wire should be bent to form a hook, which will help you to hang the wire. And then hang the wire in these hooks so that it is free to swing in the horseshoe magnet. Connect the current. Note that this is the positive terminal of a cell, so this is the positive and this is the negative. So the current is flowing in that direction. Now switch on the current and observe what happens to the wire. Then reverse the terminals of the cell. Switch on the current again and observe what happens. The direction of motion is in opposite direction. By observing the field and the direction of the current, we can summarize this by using the left hand. Stretch the first finger, the second finger, and the thumb so that they are mutually perpendicular, with the first finger pointing in the direction of the field and the second finger pointing in the direction of the current. Observe the direction of the thumb. And on the second case, when we reverse the terminal, with the current flowing in opposite direction, but the field pointing in the same direction, upwards, observe the direction of the thumb. The Fleming's left-hand rule can be stated as: when the first finger is pointing in the direction of the field, the second finger is pointing in the direction of the current, the thumb will point in the direction of the motion. not yet understood what causes a particular atom to disintegrate at a particular moment. The activity is random, and it makes no difference whether the radioactive element is pure or it is chemically mixed with another element. Heating and or cooling have no effect on the rate of decay. Experiments show that the radioactive element has a particular rate of disintegrating. This can be measured by using its half-life. Aim is to demonstrate half-life by using water and burette. Requirement: burette, stopwatch, beaker with water, lithote stand. Procedure: color the water in the beaker with potassium permanganate. Clamp a burette in the lithote stand. Fill it with water. To the brim. Open the clamp to allow water flowing out of the beaker at a reasonable rate. Allow the water to flow out of the burette by adjusting the clip. The flow of water should have a rate which is measurable. When the level reaches 0, start your stopwatch and record the value on the burette at an interval of 10 seconds. Stop recording when the level of water has reached about 50 cubic centimeters. Repeat the experiment by filling the burette with water again. Record the volume at an interval of 10 seconds again. Now, find the volume of the liquid in the burette at every time which you have recorded by taking 50 cubic centimeter, subtract the value which you have recorded. The value which you have recorded will be as shown. This is our table of results. We had the first experiment, which was the pilot experiment, experiment 1, experiment 2, then this is the average. Taking 50 cubic centimeter, which is the volume of the burette, subtract this average, we get the results here. Using these results and time, plot a graph of volume of a liquid in the beaker against time. The graph is a curve. Using that graph, find the time taken for the volume of the liquid in the bullet to change from 50 cubic centimeter to 25 cubic centimeter, which is here. This is the time, which is about 62 seconds. And find the time taken for the volume of the liquid to decrease from 25 to 12.5 cubic centimeter. Again, this interval is 63 seconds. You find that the time taken in this section and the time taken in this section within an experimental error are the same. Therefore, this time which the volume of the liquid spent to half is known as the half-life. The time taken for a given sample of an element to decrease its value by a half is known as the half-life. This time varies from an element to another. Question: is half-life experienced by all substances?
A diode is an electrical device which allows electric current to flow or to pass through it in one direction only. A diode junction is made by combining a p-type semiconductor and a n-type semiconductor in a single continuous crystal. Current flows easily from p-type or anode to the n-type or cathode, but in reverse direction only with difficulty. In these two cases, the diode is said to be on forward or reverse bias respectively. The aim of this experiment is to demonstrate forward and reverse bias of a PN junction. Requirements: diode, 2 dry cells, bulb, and connecting wires. Connect the diode in series with a bulb as shown in the figure, diode and lamp. Connect the P terminal of the diode to the negative pole of the dry cell and the N terminal to the positive pole. Then observe. After that, reverse the terminals of the diode and observe what will happen to the lamp. From the observation, when the P terminal of a diode were connected to the positive terminal of the battery, the diode conducted electricity and the bulb produces light. That implied forward bias. The positive charge applied to the p-type, which is positive charge carriers, repel the holes, while the negative charge connected to the n-type, which is negative charge carriers, also repelled the electrons. As the electrons and holes were pushed towards the junction, this one, the distance between them were decreased. That reduces the width of depression layer and lowered the barrier in potential. The interaction between holes and the electrons were allowed, and hence the flow of an electric current were made possible. That is why the bulb lighted. When the P terminal of a diode was connected to the negative terminal of the battery, this one, the diode did not conduct it, and the light doesn't produced by the bulb. That was reverse biased, because the p-type region were connected to negative terminal of the battery or power supply. The holes in P region were pulled towards the negative terminal of the power supply. Similarly, when any type connected to the positive terminal of the battery, also electrons were pulled to the positive terminal. Therefore, electrons were pulled away from the junction. That increased the width of depletion layer. Therefore, there were no electric current across the junction. That's why the bulb did not light. Because diodes conduct in one direction only, they are used as rectifiers in electric appliances. Now, what are the other functions of diodes?
Half-wave and full-wave rectification. Introduction. When a diode is connected on the AC mains, it conducts only when it is in forward biased. Hence, the current which passes through a diode is in one direction only. Due to this behavior, diode is used as a rectifier. That is, device which converts alternating current to direct current, DC. A single diode will form a half-wave rectification, while two or more diodes can be connected to form a full-wave rectification. Aim of the experiment: to construct a half-wave and full-wave rectifier. Requirements: diodes, resistor, AC generator or transformer, and a cathode ray oscilloscope. Precaution: if a double beam oscilloscope is available, the two voltage traces may be viewed and compared simultaneously. But if the CRO, the cathode ray oscilloscope, is not available, a light bulb can be used instead to demonstrate on and off situations. This is a semiconductor diode, and it is made in such a way that it has got a white band at one side. This one, the upper part. This is its drawing. It has got a white band at one side. Its circuit symbol is this one here, whereby we have a cut, just a stroke here. So it shows that the direction, the forward bias is this one. Now connect the resistor, as follows, and then connect the diode. Just here. So you have this connection, and the diode connected to the other terminal of the signal generator. The output will be connected with the inlet, and then the other part will be connected before and after. Before the diode, it will show the input signals, and if we connect after the diode, then it will show the output signals. In order to tape the input signals, we connect across the resistor and see the input. They are sinusoidal. They are sinusoidal wave in motion, as they are seen in the cathode ray oscilloscope. Then connect as follows. Connect the output in order to see the output signals. You'll see that they are pulsating waves, which the lower part, the negative part, is at cutoff. Only the positive part is appearing or emerging in the output. This is a half wave rectification because half of the wave, the positive part, is allowed to pass through. The negative part is not allowed and it is cut off. As observed, the input signal were the sinusoidal wave motion, and we had only one diode, the direction of the positive current in that one. And so what we observed as the output was the positive part was allowed to pass. The negative part was at cutoff because at that particular time, this was positive, this was negative, and so this was passing the wave. At the other part, when this is negative and this is positive, this is at cutoff. It doesn't allow any wave to pass through. So it is at cutoff. And then when it comes the positive, it is allowed to pass. So these are the waves of which you have seen as pulsating half wave rectification. In order to obtain full wave rectification, connect 4 diodes in a bridge like this. Connect a protective resistor across the bridge and connect the terminals. The output signals are as seen on the cathode ray oscilloscope. In a bridge rectifier, we obtain full wave rectification. When the upper part is positive and the lower part is negative. This diode allows signals to pass, and so we obtain the positive part passing through the diode, and the output is that one. When the upper part is negative and the lower part is positive, the upper part doesn't pass the signal. The signal passes through the lower part, but it is turned to the upper output. And so, instead of having the lower part, it is turned upside down. It comes to be like this. Again, when this comes to be positive, the upper part and the lower part negative, the upper part, diode 1, call it, diode 1 passes that wave. So diode 1, this is diode 2. Again, when the upper part is negative and the lower part is positive, D1 is at cutoff, while D2 passes the signal, but it turns upside down to the output. And so it comes to be D2 again. So always we have the pulsating wave in the positive part only. This is a full wave rectification because the whole wave is allowed to pass, as we have seen in the cathode ray oscilloscope. Conclusion: the property of a diode is to conduct only in one direction. It enables an alternating current to be converted to a direct current. Question: describe how two diodes and a resistor can be used in full wave rectification.